Hi everybody, today is lecture 17 and I will tell you about divergence and curl. These are special derivatives that you can take of a vector field, and one of them we have already seen. It appears in the statement of Green's theorem, and I'd like to explain to you why these derivatives have the names that they have. So I'll make a connection to fluid mechanics. And then using that connection to interpret these derivatives, we'll see that Green's theorem makes a lot of intuitive sense. All right, so let's get to it. So without further ado, here are the definitions. So the curl, the curl of a vector field, let's say the vector field has components P and Q. So the curl of this vector field is a function, namely the x partial of q minus the y partial of p. And the divergence of this vector field is another function. It's easier to remember. You just take the first partial of the first component and add to the second partial of the second component. Right? So today's lecture is just about these little guys, these derivatives. Okay, and the bottom line will be that when F is the velocity field of a fluid, if F tells you how fast, what's the velocity of the fluid at each point, so we're looking at a 2D fluid, maybe a pool seen from above or the stream of a river. So when F is the velocity field of a fluid, then the curl tells you how fast the fluid is rotating at each point. So the curl is a function, it gives you a number at each point. That number tells you how fast the fluid is rotating. If the number is positive, it's rotating in the counterclockwise sense. If it's negative, it's rotating in the clockwise sense. And so precisely, the curl gives you 2 times the angular velocity of the fluid at each point, right? So if you say there is so there is water flowing in front of you, you throw a little ping pong ball on the water, you're going to see it's going to move with some velocity, right? This is what the vector field tells us. The curl of the vector field tells you how fast the ping pong ball would spin if you throw it on the river, as it goes away from you. For example, so this is something very visible. You could take a marker, and before you throw the ping pong ball, you draw a little black dot on it and then throw it in, and you'll see maybe that black dot will just keep pointing the same way as when it first. So once it lands on the water, either it sits still or it rotates, and the curl tells you is just 2 times that angular rotation. The divergence, on the other hand, tells you how much the fluid is expanding or contracting at each point, right? So so for example, for something like water, which is incompressible, the divergence, if you have the velocity field of something like water, which is incompressible, then the divergence of this velocity field is going to be 0. So let's take a look at this. Let's now interpret this fluid situation more. So now that I told you the answer, let me interpret this. Understand these things, right? It's not at all clear why these formulas have these beautiful interpretations I just shared with you of rotation and expansion. So let's see why that's true. So here's how our analysis will go. We're going to start with a little piece of fluid. Maybe not, I'm drawing it quite big, but it's supposed to be not too big. So I'm looking at a piece of the fluid, a little square of fluid. It's a 2D fluid. And then let's observe that the velocity of different points, so that we have a velocity field, it's not a constant thing. So the velocity at different points of the fluid will be different, right? So all these points are moving with different speeds, and so if we wait if we wait a little bit of time, so let's say my original picture was at time t. At time a little bit later, time t plus delta t, this little square of fluid will look different, because the little points they won't travel together. They'll drift apart because their velocities are all different, right? So the square of fluid will look something like a parallelogram after a while. Right, so there you go. Okay, so the shape of this parallelogram could have a more area or less area than the original square, right? And this, so because the fluid could be expanding or contracting if you have something like air, but it would have exactly the same area as before if we have something like water. We'll see. So we'd like to relate this expansion and contraction with the velocity, with the vector field. So here F is the velocity field of the fluid, and it has a component. So it has components P and Q, right? So P is the component is the horizontal part, and Q is the vertical part. So we'd like to relate this expansion, relate the new volume in terms of the old volume and the partial derivatives of P and Q. And you're going to see that the divergence is going to appear. Another thing we'd like to do is to relate, is to look at the angle of rotation. So this square, you can imagine that it's rotating as you go around this point, and we'd like to relate this angle of rotation after times delta t with the partials of P and Q, and the answer is going to involve the curl. So let's get these partials involved. So everything here, F, P, Q, and the partials that I'm going to write down, they're all evaluated at this point over here. Okay, so here's so let's look at what happens at this point over here. Let's say, so at the other end of the square. So let's say the square has width delta x and height delta y. So at this point over here, so this is the P component, the first component of the velocity at this point, right? So we took the velocity. So the velocity at this point is approximately the velocity at the left corner plus a change that comes about because I increased x by delta x, but I didn't change y, right? This is, I can compute as dp dx multiplied by delta x, right? So the change, if I move sideways by delta x, then the derivative becomes the new value of the x component of the velocity becomes this, and the same thing holds for the vertical component of the velocity. So this height here, the q at this point is just q at the original point plus a change in q that comes about when you increase x. Let me actually move this to this other formula up. Right. So we're going to need, so for our analysis, we're going to need also the height, and so the new x, the new p and q evaluated at this other point where x is the same as the original value, but y is increased. So here p is what it was before plus the change it got when y was increased by delta y. So that's here, and q is just at this point the original height, little q, plus the amount it increased when I went up by delta y, leaving x fixed. That's given to me by the the y partial of q. Okay. All right. So now we have all these now we know we can express the new velocities at these 2 points. We can express the velocities of these 2 points in terms of the velocity at this point and the partials of the components of the velocities. Right here they are. Excellent. Now let's try to describe the new distance. So let me look now so we have these 3 points. So the blue points are where the red points ended up after time delta t passed, right? So the original distance between the 2 blue points at the bottom was delta x, but they're drifting apart, right? Delta x was the original distance between them, but the speed of these 2 points, the x component of the velocity of these 2 points, they differ by delta x, right? So they're drifting apart at a rate of dp dx delta x per unit time. The amount of time that has passed is delta t, so the new distance is the original distance plus the drift. So that was the difference in the velocities times the amount of time that has passed. Difference in the x component of the velocities. This is how the x components of the 2 points at the bottom differ. Now the y components of the 2 points in the bottom, they used to have the 2 points at the bottom used to have the same y component, but now they're different because the y component of the velocities of the 2 points are different. For here it's q, and on the right it's q plus this other value, right? So they're not going up with the same speed. One is going a little bit faster than the other. And the amount, the difference in the speeds is dq dx delta x. So here, this difference in height is the difference in the speeds. That's dq dx delta x multiplied by the amount of time that has passed, delta t. Okay. Wow, I didn't draw this other difference as small as so this point seems to have moved quite a bit to the right. Let's see by how much. So it moved to the right. So at first, the 2 points on the left had the same x coordinate, but no longer, because the x component of the velocities of the 2 points are different. And the difference is dp dy delta y. So the difference in the velocities is dp dy delta y, and the time that has passed is delta t, so the difference in their positions now is this. Here, delta t, delta x, delta y, I should stress, are small numbers. Now finally, let's look at, to complete our picture, let's look at this side over here. I'll just draw it, abuse my picture a little bit. Let's see if that's okay with the plan. Yeah, that's okay with the plan. So I'll abuse my picture a little bit. The new difference in the y coordinates of these 2 points, it used to be delta y, and then it's now different because now it's no longer delta y because of the difference in the velocities. That's dp dy delta y multiplied by the change in time. Difference in velocities times the amount of time that has passed. All right. So this is the picture I want to move, bring forward, bring to the next slide. So let's work out how much this thing rotated, right? So let's call this angle. So you see, different. The movement is not really. It's not a solid motion. It's to the contrary. You see different parts of the object rotated by different degrees, right? This right angle is different from this right angle. So what I'm going to do is I'll measure both angles. I'll measure them with opposite conventions. I'll call this one theta 1 and this one theta 2. And I will say that the rotation, so the rotation for this whole object, I'm going to declare it to be the average of these two angles. Now let's look at what the two angles are in terms of all these partials. So for example, theta 1, that's so the theta 1 is approximately, so the sine of, so theta is a small angle, so it's approximately its tangent. Right? You guys are probably used to the approximation that for small angles theta, so a small angle is approximately equal to its sine. Also, it's also true that it's approximately equal to its tangent, because tangent is sine over cosine, and the cosine of a small angle is approximately 1. So for a small angle theta, so we have this approximation over here. Now, what's the tangent? Tangent is opposite divided by adjacent. Opposite side divided by the length of the adjacent side. So the opposite side, here we worked out, so this length over here is dq dx delta x times delta t. And the adjacent side is delta x plus dp dx delta x delta t. Okay, now here's the thing. This here so delta x is a small number, but delta x delta t is way smaller, because delta t is really small, right? And if you divide a number by 0.1 or by 0.10001, that's basically the same thing. So I can approximate this derivative, sorry, this quotient. I can ignore the second part in this denominator, because the second part is way smaller than the first part. And so if I do that, I can just cancel delta t's like this, delta x's. So another way to think about this is you can bring out the delta x and then cancel it like this. You're left with 1 plus something small, and then differentiate. To divide by 1 is basically the same as to divide by 1.01. Anyway, the result is that theta 1 is approximately dq dx times delta t. Theta 2, on the other hand, which that's approximately the tangent of theta 2, is so the tangent of theta 2 is opposite length divided by adjacent length. That's this dp dy delta y delta t divided by the adjacent length, that's delta y, plus dp dy delta y delta t. So again, we can cancel the delta y's, and then we're left with 1. So here we have 1 plus something really small. To divide this number by 1 plus something really small doesn't really change the numerator. So the result is just the numerator to a first order approximation. We just get the numerator, that's dp dy times delta t. So the average angle of rotation, so the average angular velocity, excuse me, is going to be, okay, so first I'm going to write the wrong thing. So the angle of rotation, so here's something wrong. Here's what you would think is the average angular velocity. So first you take the average angle of rotation, so add the 2 and divide by 2, and then you divide by delta t, right? So the average angle of rotation divided by the time. So here's what you would think it is, right? Take the average of these two angles and then divide by delta t. That tells you how fast this object, this thing which was originally a rectangle, how fast it's rotating. Now, this is not really the right formula. We should actually have a minus sign here where I wrote plus to compute the average. The reason being, these two angles are measured with different conventions, right? So if I want to put them together and compute their average, we have to use a single convention. And here I'm using the usual one where angles are measured positively in the counterclockwise sense. So this angle over here, if I bring it to the theta 1's convention, it just becomes minus itself. I have to replace theta 2 with minus theta 2 to put the two angles in the same convention before I do any operation that mixes them. So that's the average angular velocity. So this is approximately, so theta 1 and theta divided by theta delta t, right? We have theta 1 minus theta 2 divided by delta t, and we just get dq dx minus dp dy, which is, my friends, the curl. Oops. I forgot about the factor of 2. Oh God. It's 1/2 of dq dx minus dp dy, which is, my friends, the curl of the vector field. So you see, the curl of the velocity field of a fluid gives me 2 times the angular velocity of the fluid, angular velocity field of the fluid, right? It tells me how fast the fluid is rotating at each point. So so the curl is a function, and this angle is the value of this function at this point over here. Okay, so how about the divergence, the expansion? So the new area so remember, we had this rectangle. We waited some time to pass, delta t amount of time, and then it got distorted because the velocity is of different points in the fluid the velocities of different points in the fluid are different, so it got distorted, and the area could have changed. Let's see. So here's what I'm going to do. I'm going to say that this area of this curved shape, of this parallelogram is approximately the area of this rectangle over here. Right? That's an okay. If you think about it really hard, it not only looks plausible, but that's really an okay approximation to first order approximation, right? And then the area of this rectangle is easy. It's just the area of the length of the base times the height. So let's see how much that is. So the length of the base is delta x is this much. So delta x times dp dx delta x delta t. And then the height of this rectangle is this length over here. That's delta y. Oops. That's delta y plus dp dy delta y delta t. So the result is delta x times delta y times 1 plus, right? Everything here involved delta x and delta y, delta x, delta y, delta x. I mean, you get it everywhere. And then you get a 1 for the first term, and then there are the mixed terms. So the first one is dp dx. So the first one is here. So dp dx delta t plus dp dy delta t. So that's dp dx plus dq dy. Oh, my apologies. So the height, I wrote the wrong formula. My apologies. So this here was supposed to be Q. Sorry if you had a question, if that confused you. So this here is a Q, right? So we because these points, let's look at the original picture, which was also wrong. So this height here is not the original height delta y, because the two velocities, so the two velocities are different. The original one was q, the other one was q plus a little change that comes from fixing x and increasing y, right? So the new height is the original one plus this difference in velocities times the change in time. Okay. So thankfully this number over here did not appear in these calculations. Well, actually it did over here, but I ignored it. I said it's a small term that doesn't matter. Anyway, now it will matter, and then so that here we should have had a q. Now so this mixed term, so first we had this, and then we had the mixed terms like that. That's what I just computed, times delta t, plus higher order terms, right? Things that involve two delta t's. I mean, delta t squared. I'll just ignore that. Just call it high order term. Now, so the leading change, so the new area is the old area. So it's the old area times 1 plus something that increases with time, and then another factor that changes. That increases with the square of the time. That's that's not a very big contribution for a small time. So the rate of change, so if we differentiate the area of a small piece of fluid with time, the result is going to be this. That's the speed that tells you how fast. So this is the linear term, the increase, the linear part of the increase. That's the leading part of the increase. That's the divergence. So this part here. This bracket is the divergence of f. So that's for the interpretation of these simple formulas from the beginning of the lecture, right? They're pretty simple, two terms, two partials, but I think that they're now much easier to understand, to wrap our heads around. So we now have meaning to attach to these algebraic formulas. I think at this point in the lecture, I'm much happier when I see these things than when I was before. Okay, so my next step, now we're heading towards a Green's theorem. I want to write vector versions of Green's theorem, right? We've written Green's theorem using component notation, P and Q. I'd like to write Green's theorem using vector notation. So P and Q will be implicit. And the curl is doing this for me, right? Q sub x minus P sub y, that's the thing that's on the right-hand side, on the double integral side of Green's theorem. And so we're going to write a version of Green's theorem that involves curl, and we're going to think about it for a little bit and see that it makes sense in the context of fluid mechanics. It makes intuitive sense. Then I'm going to change a sign and show you that there is also Green's theorem can also be written in terms of divergence, and show you that it also makes a lot of sense in that when we think of it in terms of fluids again. So, but before I tell you about these two versions, I have to make a few points, a couple of points about curves, right? We do line integrals. In Green's theorem, we do line integrals. And here I'd like to, in the new versions of Green's theorem, we're going to talk a lot about the unit normal and unit tangent vectors of a curve. Tangent, normal and tangent vectors. It's really vector fields you have, but they're along the curve. I'll just say unit normal and tangent vectors on a curve. So let's just do it. Here's a curve. Okay, so that's our curve. I'll call it C because I like to call it C. Here is the unit tangent vector of C. I'll call that T hat. And here is one of the unit normal vectors on C. So it's perpendicular to the tangent, right? You get one of these vectors for each point in the curve, right? So here the tangent looks like this, and so on, and they change as you go along the curve. So the normal is perpendicular to the tangent. The normal at a point is perpendicular to the tangent at a point. That tells you who the normal is up to a sign. And in the context of Green's theorem, the normal that we're going to use is the normal that's to the left of the tangent. So if the curve is closed, this normal will be the outward normal, like this. So N is the unit normal to the left of C. Okay, so we're going to be working with these vectors, T and N, and I'd like to show you what they look like in terms of a parameterization. So you can you're ready to work with them when you see them. So the unit tangent is basically, so if we have a parameterization, if we have x and y in terms of t on the curve, then the unit tangent is really easy. You just take, the velocity vector of the parameterization. Right, this tells us this is tangent to the curve. All right, so the velocity, you could just think of a particle. The velocity is tangent to the trajectory, but it's not a unit vector. So to make it a unit vector, I'm going to divide this by its length, and the length is okay. I'm going to write derivatives with a tick, so with a prime. So that's the derivative of x squared. So the square root of this squared plus that squared. That's the unit tangent. Okay, now how about the unit normal? Well, once we have the tangent, it's really easy because you're just rotating the tangent to the right, and you're 190 degrees. So the normal is going to be a vector with the property that if I do the dot product of n and t, I get 0. And okay, so there's a good way to do this. I'm just going to flip the two components, have a dy dt over here, and then a minus dx dt over here. Right, if I do this, if I flip the two components and introduce this minus sign, when I do the dot product, regardless of the scaling factor, when I do the dot product, I do this product plus this product, and then I get 0. Okay. Now there is a question of where do I put this minus sign, here or here, right? So that's the same question as which normal do I want? This one to when I rotate to the right, or the other one when I rotate to the left? Here we want normal to the left of C. Oh, can I change what I wrote here? Unit normal to the right of T. I'm kind of lightheaded today. I'm sorry. So we want the normal that's to the right of T. So as I said, the procedure to produce a normal is you flip the components and introduce a sign. So if we want to go to the right, let's say, for example, if we start with the vector with the vertical vector. That's 0, 1. So I want to get the vector 1, 0, right? So I should swap them. I get 0, 1, 0 like this, and I want to put the minus sign over here on the right, because this way it's pointing in the right direction. You see, so we do want, if I want to rotate it right, if this is t, I want this to be n, I want to introduce the minus sign here. So that's what I did. All right. Now the two, I still have to rescale the vector. I'm going to use the same scaling factor as before, because when you rotate a vector, you don't change the length. So the length of the old vector of the normal is the same as the length of the tangent when I compute them like this. All right, one more thing that's going to appear when we work with Green's theorem is the arc length element along the curve. That's just, you know, the same square root that we have here. So it's the speed of the parametrization, the length of the velocity of the parametrization times dt. And the way these things will appear in the integrals I'm about to write down is they'll appear in certain combinations. So we'll see t times ds a lot. So t times ds, when I multiply, I'm just left with the velocity of the parametrization times dt. This is the same as this vector of infinitesimals, dx and dy. And we'll also see n times ds, the unit normal times ds. And this is, and so n times ds is just, you know, so the denominator here cancels with this factor over here, so it's just dy dt comma minus dx dt times dt. Let me move this to the other side. Okay, and then this I can just, you know, say that it's a vector of infinitesimals like this. So when I see this in an integral, I can replace it with this, because as far as computations, because whenever I'm going to do a computation, I always end up replacing these two things, these two differentials, by the same thing. So as far as computations are concerned, I can do these, write things like that. This guy is equal to this, because, well, even though it's kind of illegal, it works. Okay, let's move on to vector versions of Green's theorem. So I'm going to write down two new versions of Green's theorem. They're going to look like maybe unfamiliar formulas, but in a moment I'll just show you that they're the old version of Green's theorem with new clothes. So let's do that. So the first formula, the first version of Green's theorem using in vector notation is this. You do a line integral, you integrate over a closed curve C. So in both situations we're going to have a curve C, and we have D, the region inside, and we're looking, so for each point in the curve we look at the unit normal and the unit tangent and the outward unit normal, which is to the right of the unit tangent. And we also have a vector field defined along the curve C and inside, so defined on the whole of this region D, including the border. And then the theorem says that if you integrate f times t, so that's a function, right? For each, when you do this dot product, you get a number at each point on the curve. If you integrate this function on the curve with respect to ds, as you go around with respect to arc length, then what you get, according to Green's theorem, is the double integral over the region inside of the curl of f times dA. That's the first version of the theorem. The second version is just says that the integral, if instead of doing the dot product of f with t, I do the dot product of f with the unit normal, the result is the double integral over d of the divergence of f times dA. Okay, so these are the new versions of Green's theorem. So let me just do something here. Let me resize this. I want to keep writing on the right. So the picture is this, is here. Sometimes the art gets in the way. Anyway, so we have this very nice picture. So we have two theorems. So before I tell you why these things are just the old version of Green's theorem in new vector notation, let's just think about them, these two vectors, in the context of fluid mechanics. Let's imagine that the vector field F is the velocity field of a fluid. Then what's going on here? So let's look on the right, because we just, we have fresh in our heads divergence and curl. So curl is 2 times the angular velocity at each point. Like at some points, the fluid, at some points, at different points, the fluid could be rotating with different speeds and in different directions. So over here, we're doing a double integral of the curl. This is giving me, so this gives me the average angular velocity inside d times the area of d. It's some kind of, basically you're adding these angular velocities inside. It has to do with rotation in the counterclockwise sense. Now let's look at the left-hand side. This is a number that you build by going around the curve C in the counterclockwise sense. And then for each point in the curve, so for each point on the curve, you evaluate the vector field. So you see what vector you get. Then you do the dot product with t. This gives you the component of this vector field in the tangent direction, right? If the vector field was going like this, kind of against the direction of the curve, I would get a negative number when I did the dot product. So I see how much the vector field f points in the same direction as t. That's what this dot product does. And I multiply by the length of a piece of the curve, ds, and then I add. I keep doing this for a subdivision of the curve as I go around the curve. So I'm just checking how much f is pointing in the direction of the tangent and going around the curve. And then I add all of these contributions together, and that's a line integral. So this line integral, I kind of regret moving the picture. Let me undo it. Okay, so this line integral over here on the left, it's computing. It's telling you how much f points along the tangent direction of the curve at every single point, right? It's seeing how much f is circulating around the curve. It's checking. So here I drew an example where the integral would be positive. So this is the circulation. This in fluid mechanics is called the circulation of the velocity field around this curve. And in math, we're just going to steal that terminology and just say that circulation is that integral of, if I have any vector field around a closed curve, then the integral of that vector field with respect to t times ds is called the circulation. So this is called the circulation. So, and it makes sense that the circulation, the amount that f goes around, this number that I get by seeing how much f is aligned with the tangent as I go around the curve, this has to do with rotation around the curve. And so what Green's theorem is telling me is that if the fluid is rotating inside, then inside the region, then you can see that by going around on the boundary, right? It's relating some statement on the inside of the region, the situation on the inside of the region with what's happening outside. And it's not really, it's not unbelievable that these two numbers are the same. At least they connect to rotation in the same way. So the other version of the theorem is this one. So it involves the flux of the vector field out of this curve C, across this curve C. So we're going to talk about flux in the next lecture, and where I'll also give you examples of how we use these theorems. I'll give you an example, at least how we use the bottom one. The first one is basically the same as before, as you guys will see in a moment. So flux. So let's think about what's going on the left here, right? So F is the velocity field of the fluid. So the fluid is moving this way, right? So here, if it's moving this way, if you look here and it's moving this way, the particles at this position, if you wait a little bit of time, they're going to leave the curve. If you just wait enough. On the other hand, here, if the fluid is pointing this way, the fluid particles are entering this curve, entering the region D. Right, so this flux has to do with how much fluid enters and leaves this region D. Right, we're going around the curve, and then we take F and we ask, is it pointing in or out, and by how much? Right, we do the dot product with N. This gives me this direction over here, and this number, this length over here, is just how much the fluid is leaving, or is a measure of how much the fluid is leaving or entering the region at that point. Right here, the tangent would be this, the normal would be that, and the vector field. So here's normal. The vector field would be here, and you see you get a negative number. So negative number is so F times N would give me a negative number when the fluid is entering. So this is the flux out of the region. Flux of F out of the curve C. Again, we'll get back to flux at the beginning of next lecture. And it's not surprising, I think, that the flux that the flux can also be computed in terms of divergence. After all, divergence tells me how much the fluid is expanding at each point in this region D. And if I know how much it's expanding at each point, so the expansion, the sum of the expansions inside the whole region, that should match by conservation of matter, the flux of matter, the flux of fluid out of the region. If I know how much it's expanding at every single point, all that expansion has got to go somewhere. It's got to cross the boundary, and that's what the left-hand side of the theorem is telling me. So I think the divergence version of the theorem is the easiest one to wrap our heads around. So to conclude the lecture, let me show you how these two theorems are just the old theorem in fancy notation. So the first one is, so here's the first one. We're looking at the integral over C of F times T ds. Right, so a while ago, so F, let's say it has components P and Q, and T times ds, just a moment ago, let's go back, T times ds is just dx comma dy. Right, when I'm going to integrate this, I can just replace T times d. I integrate T times ds in the same way as I integrate dx comma dy. So let's just replace it with dx comma dy. So this is the same as the integral over C of p dx plus q dy. Okay, now integral of p dx plus q dy over a closed curve C. The field is defined in the interior of the curve, so that's the double integral over d by the usual version of Green's theorem of q sub x, that's the x partial of q minus the y partial of p. But this is just the curl of f, right, by definition of curl. And so we're happy, right? The left-hand side of the new version of the theorem is the same as the right-hand side of the new version of the theorem. I should take this opportunity to observe one thing, that dx comma dy is this vector dr, right? The infinitesimal. So t times ds is the same as dx comma dy, which is the same as dr. So there are many, many ways to write down integrals. Here, so for example, this part over here could have written dr over dt times dt, and then this part I could have just written dr. So do bear in mind that if you see an integral with respect to dr, that's the same as an integral involving the components of the vector field, p times ax plus q times dy, and that's the same as the integral of the vector field dot t times ds. Now let's look at the other one, the integral over c. So the version with divergence, so the integral over c of f times unit normal times ds. So f, as before, is just has components p and q, and n times ds is just dy comma minus dx. Okay. So dy comma minus dx. So now, let me just write this down. That's the integral over c of p times dy. Let me actually put the thing in front of dx first. So we have q times minus dx. So you get minus q times dx plus p times dy. And then I ask you, what does Green's theorem tell me about this line integral? And well, the answer is Green's theorem tells me this is the same as the double integral over the region inside the curve of the x partial of the second component. So that's dp, so ddx of p minus the y partial of the first component. Times dA. So you see I just get p sub x plus p sub x plus q sub y, which is the divergence of the vector field. So again, I recover the old version. I mean, using the old Green's theorem, I was able to prove this new one. It's basically a way of how. So you have to choose where you put a minus sign. So when I gave you the original version of Green's theorem with components, I chose to put a minus sign over here, but I could have also put it in the first component. So on the line integral side, right? And then you'd have a plus on the double integral side. Anyway, thank you for listening. I hope you find this stuff as exciting and amazing as I do. And I will see you guys next time.